Okay, I'd like to go over this worksheet that I made for you all. There was one thing that was slightly off on this. I probably should have put in a number 59 right there, just so you had some more guidance on that particular problem. I don't have a huge amount of time right now, so I'm just going to show you the answers relatively quickly. Okay, so we're talking about palladium on the first one. Palladium is right here. Atomic number of 46, if you can't see that, sorry, 46 right there. Okay, so 46, that's how many protons you have. 100 minus 46 will give you the number of neutrons, that's number 61. Since you have a positive charge, you have fewer electrons than protons, which gives this 44 electrons. Next, atomic number 28 is nickel right here, so Ni. As I said, I should have probably given you that. Protons should be the same number as the atomic number, so that should be 28. 59 minus 28 would give you 31. If we have a plus 3 charge, then we have fewer electrons than we do protons, and therefore this should be number 25. Okay. Next, 16. 16 is sulfur. It has 16 as the atomic number. The atomic mass should be protons and neutrons together, which should be 32. Now, it gave you 16 protons and 14 electrons. Sulfur should have a minus 2 charge, but in this state, 16 minus 14, that is actually a plus 2 charge. Don't make my mistake, well, which I kind of did that on purpose, but be aware of that and look for things like that. Okay, 38 protons. That is strontium down here at 38, so Sr. Okay, atomic number is 38 as well, because that's the number of protons. 88 minus 38 is 50. And if you have 36 electrons versus number of protons, that will again be a positive 2 charge. Iodine, number 53. Okay, 53 is the atomic number. That's the same as the number of protons. 127 minus 53 gives you 74 neutrons. There's one more electron than there is protons. That's what gives rise to a negative 1 charge. And finally, nitrogen. Nitrogen has an atomic number of 7. That's the number of protons. Neutrons and protons together give you the atomic mass of 14. Now, we've got negative 3 charge, protons, there's 7 of them. We need 3 more electrons, so 7 minus 3, or minus 10 will give you a minus 3. Okay, next section. Iron 3 sulfide should be Fe2S3. This is cobalt 2 chloride. Sodium oxide would be Na2O. It's a subscript of a 2 there. Calcium oxide would simply be CaO, because the plus 2 and the minus 2 cancel out. Zinc 1 fluoride is simply ZnF. This is molybdenum 2. Chloride, CHLORIDE. Barium chloride is BaCl2. Back up here. This is aluminum oxide. Now this is called copper 3 sulfate. Sulfate is a polyatomic ion. This should be Cu2 parentheses SO4 3. Calcium hydroxide, okay. Aluminum phosphate, both of those have a +3 and a -3 charge there, so that's just AlPO4. Now we've moved on to covalent compounds. Carbon tetrachloride is CCl4. This is sulfur dioxide. And this is nitrogen trichloride. Okay, page 2. Let's do Lewis dot structures, molecular geometry, and intermolecular forces. You may find that you need to do several steps in between that. That is perfectly okay. Okay. Again, I'm going to rush through this, sorry. We've got C, H, Cl. There is a dipole moment this direction. Okay. Molecular geometry around the carbon is tetrahedral. That is a polar molecule, which means that there are dipole-dipole interactions. Okay. I apologize, I didn't specify which one in this case to look at, but this is CH3OH. Around the carbon, that is tetrahedral. Okay. However, this is where the dipole moment is going. And as a matter of fact, this O and H have a hydrogen bond, so that would be hydrogen bonding. Remember, whenever you have a hydrogen bond, that's because hydrogen is directly bonded to oxygen, nitrogen, or fluorine. Okay, the last two down here. Got silicon. Molecular geometry is simply linear. This is nonpolar because the oxygens pull in equal and opposite directions. And so this would be dispersion or London forces. Okay. And here we have PCl3. This is not going to be, yes, there's some polarity here, but it's not huge. So just so you know, that's not a huge pull there. So tetrahedral is what this phosphorus would be, and that would still be considered a dipole-dipole, but it's a weak dipole-dipole. Okay. Last page. So we're going to define the following molecules as polar or nonpolar and determine the intermolecular forces between like molecules. So again, you should probably do the Lewis dot structures first and then look at things. So if you're having confusion at that point, then, or with these answers, you might want to go back and try that. Okay, so CH4 is kind of the definition of, sorry, I hit a bump, nonpolar. Okay, so it would be dispersion forces. The point of this is to show you that when there's nonpolar, that's a dispersion, things like that. This is a polar molecule, and so it will be a dipole-dipole interaction. NaCl, threw this in here, make you realize that that is not a covalent compound. That is an ionic compound, and therefore it's in a whole different category. Okay. Last three. We just did this guy. That is a polar hydrogen bond, right? So this would be hydrogen bonding. HF is polar hydrogen bond. Again, this is a hydrogen bonding. And most importantly, water. Remember how it's bent? It is the definition of polar. Okay? And it is definitely in the category of having hydrogen bonding. Thank you.